Thank you, Leslie. Thanks for the introduction. I'd like to thank the organizers for inviting me here, and the Simons Institute for the hospitality. It's great to be here, not only at this workshop, but this whole semester. So this is not going to be accounting talk. And in a nutshell, we'll move from the sums of product simmering to the tropical simmering. So in more detail, we'll be interested in the following question. Which discrete optimization problems can be solved exactly or optimally using a fundamental algorithmic tool, namely linear programming? And we will not be interested in individual problems, but in classes of problems. And the framework of constraint satisfaction problems we've heard quite a bit about this week, and this whole semester will allow us to do so. And the ultimate goal is to obtain unconditional characterizations of the power of LP for discrete optimization problems. And by unconditional, I mean characterizations that do not depend on P versus NP or P versus Sharpie and so on. But, well, this is a classification workshop. As a corollary of these characterizations, we often obtain some complexity classifications. So this is a survey-ish talk, say recent work from last 4 years or so, including some very recent work, and everything I'll talk about is joint work with the Johan Tappe from Paris. So let me start with two motivating examples on which hopefully you'll get used to my notation. And one of them hasn't appeared before. This is the advantage of giving a talk that is not on counting. So this is the ST-min-cut problem. You are given a graph, two special vertices, S and T, and you want to find an ST-cut. So a subset of the vertices that includes S, excludes T, and minimize the number of edges going across. So one way to formalize this problem is in the following way. It's an optimization problem where we have n variables corresponding to the vertices of the graph. Each variable can get one of the two labels, 0, 1. And the objective function is written on the slide. So what are these? So this term in the objective function makes sure that S gets assigned 0. So it's a unary function that returns 0 if its argument is 0 and infinity otherwise, written in a slightly cryptic way. And similarly for T, again, this function makes sure that T gets assigned 1. And the third part of the objective function is the sum over all edges and makes sure that every edge that goes across is counted. And we know a lot about this problem, obviously, everyone. But one particular feature I want to emphasize here is that if you write the natural linear program relaxation of this problem, it's going to be tight. So you can solve this problem using a natural linear program relaxation. My second example is the vertex cover problem. So you are given a graph, and you want to find a cover, so that is a subset of vertices so that every edge is covered. One of its two endpoints, at least one of its two endpoints is touched. And you want to find a cover of the smallest size. So again, you can see there's an optimization problem in the following form. N variables corresponding to the vertices of the graph, two labels to be assigned. 0 means out, 1 means in the cover. And the objective function here, so the unary function sitting on all vertices of the graph count the size of the cover. So if a variable or vertex gets label 1, then it's counted for, so that's the 1. And the second part of the objective function makes sure that it's indeed a cover. So it's not allowed to have 0, 0 sitting on an edge. And again, we know quite a lot about this problem. But one particular feature I want to emphasize here is the fact that if you write the natural linear program relaxation for this problem, it's not going to be tight. It's not very surprising. But this is the motivating question for this work. Why is it the case that linear programming solves the ST-min-cut problem and doesn't solve the vertex cover problem, apart from the obvious reason we know about? And it's fair to say that we know quite a lot about these particular linear programs, the vertex cover linear program, relaxation, and the ST-min-cut. So, I'm interested in this question in a broader sense, for interesting classes of problems, not just these two problems. How do we do it? Well, we'll use the framework of constraint satisfaction problems. So here's a definition, and then I'll comment on it and relate it to other definitions. So an instance of a valued constraint satisfaction problem, or VCSP, as I tend to call it, is the following. So we'll use this useful piece of notation. Q bar is all rationals together with positive infinity. And an instance, a VCSP instance given by n variables, x1 through xn, a domain, the set of labels or values, if you like, and an objective function that is given explicitly as a sum, say, of q terms, and each term is a fixed array function. So there's notation, x1 through xn are the variables. These bold B's are the scopes. The variables, say, the ith term in the objective function depends on. And the range of the function is q bar, rationals and infinity. And the goal is to find an assignment of labels from D to all the variables that minimizes I, the objective function. So the example we saw on the previous slide, the vertex cover problem. So the variables are the vertices of the graph. The labels are just 0, 1. The objective function is as we saw before. So it has mod of V plus mod of E terms. And in the literature, so CSPs are a hot topic, as you may have observed this week, for people who are not part of this program. There are a lot of definitions of CSPs, a lot of papers on CSPs. People mean very different things when they talk about CSPs. So let me comment on this definition. So in the sort of so-called algebraic approach to CSPs, this is the standard terminology. So CSPs, or decision problems, corresponding to questions equivalently, is there a homomorphism between two relational structures? It fits in this framework if you enforce the condition that the range of all functions is just 0 and infinity. There's no optimization involved, and the question is just asking for the existence of a, say, feasible solution. If you enforce the range of all functions to be 0, 1, you get so-called min CSPs when you minimize the number of unsatisfied constraints. This will be interested only in exact solubility. This is the same as saying maximizing number of satisfied constraints. Each constraint could have little weight, non-negative rational number, so it corresponds to the third case. But still, it's the case that every function has only two-value range, two-value codomain. Now, the penultimate on the list is the so-called finite-valued CSPs, where the range of every function is the set of rationals. So this encodes a lot of optimization problems. And finally, the one I've defined, it's called valued or sometimes general valued, to emphasize the fact that it includes the first case as a special case. Valued CSPs, where the range of all functions can be Q bar. So there's a lot of recent breakthroughs and results in the approximation community. So let me comment on their approach to CSPs. So they often deal with maximization problems because, well, for approximation there's a big difference, of course, between minimization and maximization. For us, for the purpose of this talk, there's no difference because we care about exact solubility. Most of the papers actually deal with the so-called Boolean domain, where D has just two labels. In fact, most of the papers also deal with the 0-1 valued functions only. And there are very few results in the approximation community where they can say something where you allow infinity. So when it includes the crisp CSP or decision CSP as a special case. So often here the results tend to be stronger, but for a smaller framework. But we really do want to include CSPs as a special case because it's an interesting framework capturing so many nice things. Okay. No questions so far? So question is, which VCSPs are solved exactly by linear program relaxations? So what do I mean by linear program relaxations? Let me give you a definition of a linear program relaxation. So this is, again, the objective function we want to minimize. And there's a natural way how to write a linear program relaxation. So natural that everyone came up with the same linear program relaxation in independent papers. It's called the basic LP relaxation, or the standard, or the natural, and so on. So what is it? So the intuition is that, so this is just a piece of notation, that you have two sets of variables in the LP relaxation. How do I call them? Mu's and lambdas. And mu's are indicator variables indicating whether the ith variable, xi, gets assigned label A or not. So it's a 0-1 valued variable. And similarly, lambdas are indicator variables for the ith term in the objective function being assigned partial assignment sigma, where sigma is of the appropriate length. And then the linear program relaxation just relaxes these variables from being 0-1 value to being between 0 and 1. We think of them as probability distributions, so, well, they better be all non-negative. They should sum up to 1. In fact, they are not all written there, but this implies the other. So similar sum should be written for lambdas, but it's not needed. It's redundant. And the objective function is just the expected value of the original objective function with respect to these probability distributions. So the only interesting set of linear inequalities in this LP is this last one, when we say how the mu's and lambdas interact. So if you take, say, the jth term in the objective function, and you take one variable sitting there in the scope of that term, xi, and you look at the label that can be assigned to this variable, and if you marginalize onto this pair, xi and I, which is this sum, you get the same value that mu sub I of A gets assigned. This is marginalization. And a useful piece of notation here is that if I have a function phi, I denote by dom, the domain of phi, the set of assignments that make it finite, so sort of feasible solutions. So this part of the linear program makes sure that infeasible solutions, partial solutions, get assigned 0, so they are never part of a solution. So that is a linear program relaxation. Sometimes it works, sometimes it doesn't. Later on I'll show you a result exactly when it works. But if it doesn't work, there's a standard way of making linear program relaxation better by throwing in more inequalities. And one of the standard ways is this Shirley-Adams hierarchy. Usually it has just one parameter. I'll tell you in a second why I have two here. So you can think of K and L being equal. Say the kth level of the Shirley-Adams hierarchy is start with the BLP and throw in all linear inequalities that involve at most K variables. That's the idea. And as long as you keep K constant, this is still a linear program of polynomial size, and you can hence solve it in polynomial time. In fact, this LP relaxation has a nice description because now I don't consider mu's and lambdas as two sets of variables. They'll be all called lambdas. And the two parameters have the following meaning. So L, the larger one, or not smaller than K, it's required that every subset of, say, at most L variables has a term in the objective function. So if there is not such a term in the objective function of the optimization problem we care about, you can always throw in one with, say, the constant 0 function. So it doesn't change the complexity of the problem. Now, so the variables of the linear program relaxation are called lambdas for every term in the objective function and every assignment to this term. And again, the linear program looks very similar. We think of these lambdas originally as a 0, 1 valued indicator variables, whether the ith term gets assigned sigma. We relax them to be between 0 and 1, so they better be non-negative. We think of them as Polter distributions. The infeasible solutions get assigned 0, and they should sum up to 1. Now the marginalization constraint, previously it was looking at, say, the ith term of the objective function onto one variable. Now it's slightly more complicated, but not much. We marginalize onto variables of size at most k. So the intuition is that we have these parameters k and l. If you have a constraint on L variables and you look at the subset of variables in the scope of size at most say L, so K, then and you marginalize out onto these variables, it's the same value as you would get for the corresponding LP relaxation variable on those K variables. So in this notation, PLP is just SA11. The reason why we have two parameters, it allows us to obtain slightly stronger results than just having one parameter. But as I said, if you are familiar with the Shirley-Adams hierarchy, just think of K and L being equal. Okay. So this is a relaxation. So if you have a VCSP instance and you write down its Shirley-Adams relaxation, and if you solve it, the optimal value of the linear program is a lower bound on the optimum value of the discrete optimization problem we start with. We are interested in the case when this inequality is tight. So when it's equality, we say that the relaxation works in this case. And again, the main question of this work is to answer for which class of VCSPs this relaxation works. When did I start? Was it past? Yeah. Okay. Good. So we won't be able to answer this question in full generality, but we'll answer for an interesting and large fragment of VCSPs. In fact, in many of these talks we've heard this week, this is the fragment of CSPs or Holland or VCSPs people talk about as the default one, the only one, in fact. It's the most studied one. It's the one when you naturally parameterize by the set of allowed functions or relations in your instance. So this notation VCSP of gamma is where gamma is a finite set of functions on some fixed finite domain D. It's just a set of all instances where all functions come from gamma. So slightly specializing this question will be interesting when for which valid constraint languages, set of functions gamma, the Shirley-Adams hierarchy works. And we'll be able to answer this question. Okay, so the main result, maybe two results, which you'll see towards the end of this talk will look like this. Let gamma be a valid constraint language of finite size on some fixed finite domain D. Arbitrary D, not Boolean, not 3-element, any finite domain D. then gamma is solved by SAKL if and only if some condition. So the condition is going to be algebraic. So I'll spend the next 10 minutes explaining the words that are used in this theorem. But if you saw Andrej's Bulatov tutorial at the boot camp, he talked about invariants. Often when we can identify some invariants that are preserved by computational complexity, then we can get some handle on classification. And so these properties I'll talk about, these algebraic properties, are of that form. They are invariants. Okay.
Can I ask?
Oh, yeah.
So if K is a parameter,
yeah.
Would you get some results on the complexity when so if K goes, so for the, let's say, for fixed K, let's say, a problem does not have such expression using this. So if you change the K, can you somehow, if the K is parameter, can you say something when a problem suddenly has a good description?
Right. So as it turns out, the result is that if SAKL works for some fixed constants KL, it will work for K equals 2 and L equals 3. So it's sort of a collapse of hierarchy. So that should partially answer your question, right? That's going to be on slide number 25 or something.
Okay.
Any more questions? Now you know about it, so maybe you can leave now. Any more questions? Okay. So let's talk about these algebraic properties that will be used in the statement of the main theorem. So the first one are polymorphisms. So polymorphisms are algebraic properties that are preserved by decision CSPs. And the idea is very simple. The idea is that if you have m feasible solutions, an M-ary polymorphism is an operation that takes these m feasible solutions and produces a new feasible solution. That's it. A formal definition, so it's an M-ary operation. So this is the domain of the problem. So this f is a polymorphism of a function phi if the domain of phi, so there's notation for the feasible solutions, goes under f. So in particular, if x1 through xm are feasible solutions, and you apply f to these x's component-wise, you get another feasible solution. So here are some examples that hopefully help to people who haven't seen polymorphisms before, even though I don't think there are many people like that here. So projections, or sometimes called dictators, are trivial polymorphisms. If you get, so projection is an operation that returns one of its arguments, say the first one. So if you take m feasible solutions and your operation component-wise returns always the first one, well, by assumption you returned a feasible solution. These are not very interesting polymorphisms. In fact, the Fedor-Edwardes dichotomic conjecture can be stated in the way you are tractable if and only if you have other types of polymorphisms, less trivial. Now, if a function is finite valued, so q valued, there are no infinities, observe that any operation is a polymorphism, because any solution is feasible. There are no infinite values. And a less trivial example, so here's a clause, that's a horn clause. It has one, and hence at most one, non-negated literal. And you can see it as a function returning 0 or infinity, so it returns infinity on only one of the 8 possible tuples. And it's easy to check that actually these kind of functions coming from horn clauses have the binary min operation on 0, 1 as a polymorphism. And it's one of the reasons why horn set is actually tractable. Okay, so these are polymorphisms. They are algebraic invariants of decision CSPs. They are not good enough for optimization. We need something more general. We need weighted polymorphisms. So the name changes every other day. Sometimes they are called fractional polymorphisms, sometimes weighted polymorphisms. I guess tomorrow there's the F. So what is the idea? The idea is that you start with polymorphisms. And a weighted polymorphism is a probability distribution on polymorphisms, so that the following holds. So if you look at the expected value of a solution with respect to this probability distribution, it's not worse, because we are minimizing, than the average of the m feasible solutions you started with. So you don't need the expected value, it just makes the notation on this slide tighter and slightly nicer. So here's the formal definition. You start with a function phi. You look at the set of its M-ary polymorphisms, finite set. And a probability distribution on this set is a weighted polymorphism if the following is true. If you take any m feasible solutions, so m assignments that make the function phi finite value, not infinity, the following inequality holds. On the right-hand side, we have the average of these m solutions. And on the left-hand side, we have the expected value. So it's the sum over all operations f, MRE operations of f on D, and the probability of the distribution times the value of phi of f applied component-wise again on these m feasible solutions. And if you've never seen these objects before, they seem strange, but here's an example that most of you should know about. So the concept of submodular is key in discrete optimization, and one of the definitions of a submodular function is the following. So a submodular function phi, defined on 0, 1 to the r to q bar, is submodular if for any two r tuples x and y the following inequality holds. So often they are defined equivalently using intersection and union. So min has the role of intersection and max has the role of union. And this is a weighted polymorphism of phi, which assigns probability half to min and half to max. So this important concept of submodularity fits here as a very special case. So that indicates that these objects are perhaps interesting. Questions? Okay. So here's the first theorem. So last piece of notation, hopefully. If you have a gamma, a language, so it's a set of functions on some fixed finite set D, we denote by support of gamma the set of operations that get assigned strictly positive probability in some weighted polymorphism of gamma. So if gamma was, say, the set of submodular functions, certainly min and max would be in this set, but more operations as well. An interesting feature of this object is that it's a clone. So it's closed under composition, functional composition, and it contains all projections. And one of the earlier results on this line of work, jointly with Johan Tupper from a few years ago, is the following. If you have a valid constraint language on any fixed finite domain D, the following two are equivalent. Gamma is solved by BLP, which means that any valid constraint satisfaction problem instance, where the functions in the objective function come from gamma, is solved by BLP. So the BLP relaxation is tight. If and only if, for every m at least 2, there's an MRE symmetric operation, so operation that returns the same value if you permute the arguments, in the support of gamma. So, well, it's fair to say that this condition, despite being this being a precise algebraic characterization, is it's not even known to be decidable. If I give you language, it's not clear how to test for this condition. But nevertheless, it's very powerful. So I'll give you one or two examples.
Is it sorry, can I ask you, this with omega, that's an exists? It means support of gamma is the set of f such that there is...
Yeah, such that there exists omega, a weighted polymorphism of gamma, and that gamma assigns a positive weight to f. Thank you. Questions? So here's an example. So a binary operation is called semilattice, and think of min or max as a good example, if it's idempotent, commutative, and associative. And if you have a semilattice operation, which is by definition a variety 2, you can build symmetric operations of arbitrarities, as you would do with min. So this expression is the same as if you had binary min. You could build MRE min by doing this. Compare the result with the third option, and so on. And because of this construction, and because of the fact that the support of gamma is a clone, we immediately get, as a corollary of the previous result, that if you have a valid constraint language that has a semilattice operation in its support, then any VCSP instance built over this language is solved by BLP. Why is this useful? Well, it captures all submodularity. So this is, again, the definition of submodular functions you saw before. And this is the usual definition, equivalent to talking about subsets and intersection min and union. But there are more general definitions of submodularity. So there are functions in the literature studied which talk about submodularity on lattices. So this corresponds to the case when the lattice is distributive, but you can study submodular functions on not necessarily distributive lattices. You get the same kind of inequality. Just the min and max is replaced by mid and join. There's this concept of case submodularity, where the underlying structure is not a lattice, but it's a tree, and the two operations which are called here actually it's a star. It's a special case of a tree. Again, some binary operations, mid and join like. There's this other notion of tree submodularity, where the underlying structure is a tree, and you define appropriate mid and join. And all these functions are defined in terms of some inequalities, which are weighted polymorphisms. And in the definition of the equivalent operation, there is a semi-lattice operation. So by the previous corollary, all these problems are solvable exactly in polynomial time. So this is the slide where I'm supposed to pause and say something about the proof. Do I have time? Okay, I have some time. So these weighted polymorphisms, symmetric weighted polymorphisms, are exactly what you want when you want to show that a linear program relaxation is tight. So if you have weighted polymorphisms, these symmetric, okay, if you have symmetric operations of all RTs from 2 onwards in your support, and if you get an LP solution that is not tight, it's a rational solution. You can make sure that all the denominators in the fractions are M, and then you apply MRE symmetric, you apply a weighted polymorphism that involves an MRE symmetric operation, and because the inequality is the right way, you get a solution that is not at least as good as the previous one, and that's one of the reasons why it works. The other direction, you use linear programming duality. And again, this condition is not known to be decidable, but nevertheless, apart from the generalizations of submodularity being tractable as a corollary of this result, you can show other interesting results. So in particular, I like very much this one. Magnus Wallström from London managed to use this result to design efficient FPT algorithms. Okay. So BLP solves a lot. It's natural to ask whether it solves everything. The answer is no. There are problems, in fact, simple problems corresponding to, say, permutations that cannot be solved by BLP. So you can ask, is there an interesting class of problems for which BLP solves everything? It's this concept of universality. Ginny talked a lot in his talks. And it turns out the answer is yes, and here's what it is. So if you focus your attention on so-called finite valued or Q-valued constraint languages, so no infinity allows, these are purely optimization problems, then the result from a few slides ago can be strengthened. And then for gamma to be solved by BLP, you only require to have a binary symmetric operation in your support. So not symmetric operations of all RTs from 2 onwards, but just the binary one. So this is decidable. This is easily decidable using linear programming again. Can be checked for. And as it turns out, for these languages, for Q-valued constraint languages, these are the only tractable cases. So the result here says that if you have a Q-valued constraint language on any finite domain D, either gamma admits a binary symmetric fractional or weighted polymorphism, or gamma is NP hard. In fact, this is slightly red herring. What we actually show is that if you don't admit this object, then gamma can express a max-cut-like function, and that one can not be solved by BLP. So in other words, even if P was equal to NP, under the first part of the theorem, those cases are solved by BLP, and the rest is not. Well, if P is equal to NP, then you can solve them in other means, but not using BLP. So in some sense, this theorem is independent of P as NP. So this is what I was hinting on at the beginning of the talk. But it just happens to be exactly like max-cut, so you easily just get a reduction if you care about this distinction. So it's fair to say that this result, even though it's not 100 plus pages, it's maybe 37 pages in the final version, it was some work, and there's some list of previously done cases. So most of the previous works were case analysis, because it wasn't quite clear what to do, but many of them are very non-trivial and very technical results. But here, the key idea was to, well, one of the key ideas was to use this algebraic framework, use a weighted polymorphism, some invariance that is preserved by polymorphism, and in fact also by algorithms, which is not necessarily the same, and then hammer it. Okay, so the second result I want to talk about is this power of Shell-Adams hierarchy, not the BLP, which is the first level, but higher up. This is just the reminder of the notation for the support of gamma. And so this is the theorem. So it looks very similar. Let gamma be a valid constraint language on arbitrary finite domain D. The following 3 are equivalent. So maybe they're in slightly weird order. So gamma is solved by SAKL for some fixed KL. So there's an existential quantifier missing. If and only if, in fact, if it's solved by SA23, so say the third level of Shell-Adams, if you don't care about the distinction between the 2 parameters. And this is if and only if the following condition is true. So this time, for every M at least 3, rather than at least 2, there's an MRE operation in the support of gamma that is weak near unanimity. Not as bad as derectangularizing sequence, but it's still pretty bad. So what is it? So an operation is called weak and U if all of its arguments, but at most one, are the same, then the answer doesn't change. And interestingly, if I give you a language, gamma, it's decidable to test whether this condition holds true. Here we know how to do it. And it's actually very simple. Okay. So is it useful? It turns out it's, again, very useful. You can prove tractability of languages that were known before using more complicated algorithms. You can prove tractability of languages that were not known to be tractable before. For instance, so to give you one-line proof, if you have a language that has the majority operation, so it's a ternary operation returning, you know what, it's a majority, in the support, then gamma is solved by SA23. What is the proof? Well, this is how you generate an Emery weak NU operation from the ternary one you start with, just like that. Just ignore the M minus the arguments. So this is just what was known before, some very special cases. Again, similar construction. If you have in the support a tournament operation. So what is a tournament? Well, it's an operation that is conservative and commutative, or symmetric, if you like. And on a two lines, you can argue that it generates Emery weak NUs of all RTs, and hence SA23 solves. Again, so this is some hint on the proof. So the sufficiency of this condition is what we did last year at ICALB, and the key idea is there to observe that if you have a solution to your LP relaxation, you can find a solution where the support of it is close under all polymorphisms, and then you do complementary slackness. It's not very difficult. It's maybe 2 or 3 pages, but surprising, I would think. The necessity is the other paper which is now submitted, and there we use where we rely heavily on these strong results in the CSP committee, in particular in this result characterizing bounded width by Andrei Bulatov, and also independently by Barta and Kozik. Okay, and that's where the collapse come from. This collapse that's part of the result for decision CSPs. Okay, so again, this is stronger than BLP. This is the strongest polynomial size Shardam's relaxation. Does it solve all VCSPs? The answer is no. Can we find an interesting class of problems for which it is a universal algorithm, solves everything that can be solved? It turns out that there is a class like that, and it's a class, the set of valid constraint languages that can express, and by express I mean being an instance, VCSP instance over that language, a unary function that is injective. So it's finite value, there is no bar here. It's injective, so mapping different values to different domain values. And if you have such a useful unary, then it is the case that there's a dichotomy. So either gamma is solved by SA23 or it's NP hard. In fact, again, we prove here something slightly stronger. We can show that what happens, you can express or interpret in this sense. So this interpret, I'm not going to develop it, but it's something more general than being expressible. This comes from, again, a decision CSP, so it's a PEEP interpretation in a valued world. Can interpret something that SA23 cannot solve, namely equations. So that's the thing that cannot be solved. And once you have equations, and once you have an injective unary function, you can get NP hardness. Well, this seems like a slightly odd class. It's a language where you say, well, it's a language over which you can express these things. Are there any interesting cases? Turns out we know of 2. The first one was mentioned before, at least in 3 talks, and this is the conservative VCSP. So a language gamma, it's called conservative if it contains all 0-1 valid functions. In particular, it contains an injective unary function. You can build it. And hence you get a dichotomy for this. But this is not a new dichotomy. This dichotomy was obtained, in fact, by Vladimir Komologov and myself years ago. But the interesting feature of this new proof is, well, several. Firstly, the proof is significantly simpler. The contribution in this paper was the algorithm. It wasn't known that case was tractable before. It was a different criterion. And also the hardness. So both were rather technical. Here the algorithm is very simple, natural. and the hardness is it's a half a page proof. And it also gives it's not stated here this way, but as a corollary of this theorem, you get that the tractability criterion for this dichotomy is different than it was before. There's a majority operation in the support, which is very simple. The previous one was, well, ask me after the talk if you want to know. And the second corollary is the class of problems known as minimum solution problems. So it's problems where you have only relations, so I would call them zero infinity valued functions. And the only thing that allows you to do some optimization is, well, guess what? Injective unary function. So where does it come from? Over the Boolean domain, these problems are called min-ones. You have set of relations you want to satisfy plus minimize the number of variables assigned 1. This is a generalization to larger domains. It includes as a special case, say, bounded linear programs and other problems. And again, as a corollary of the dichotomy from 2 or 3 slides ago, if you have a min-sol language, set of relations, plus an injective unary on any finite domain D, either this language, well, the VCSPs built from this language are solvable by SA23, or this language is NP-hard. And again, the NP-hard means can express something that cannot be solved by SA23. So even if P was equal to NP, it would not be solved by this particular algorithm. So this problem was studied before, and again, there were some special cases known before. And again, many of these results are very non-trivial. But again, the key was to use this algebraic approach to get a dichotomy for all possible domains. Some of these papers, like this one, actually also deals with approximability. So it's fair to say they contain also a lot of other results which we do not generalize. This is just about exact solvability. Now, are these problems interesting? With these, just relations with a single injective unary finite value function. Well, it turns out that if you relax this condition, if you allow this, okay, which letter is it? Is it mu or mu? If that function is not injective, you get all VCSPs. So this condition cannot be relaxed. Otherwise, you would get a dichotomy for all VCSPs, and hence for CSPs, and you've just solved the Federer-Vardy conjecture, and you can go and celebrate. Okay. So I'm pretty much done. This is my last slide. So what you've seen is, but it's probably not too surprising to people who are going to say on these Holland problems because they have similar theme. In order to get a dichotomy for an interesting class of problems, look at some algorithm. There are not that many algorithms known. Strong algorithm. Try to capture what it can solve. In this talk, it was LP relaxations. And then obtain, if possible, a dichotomy for a class of problems where this algorithm is a universal. It solves everything and can be solved. And one last feature I'd like to emphasize that these invariants Andrei talked a lot about. In this talk, these were polymorphisms and weighted polymorphisms. They were studied before for capturing the complexity. But it doesn't imply that they can also capture the power of certain algorithms, because those are different things. But they do in this case, luckily for us. So that's it. Thank you very much.
Questions?
So how do your results relate to, say, things like polymatroids, which are linear programs where the integer program can be solved by linear programs?
Need more than a few seconds.
All right, here's another one for you.
Okay. Let's see what I can do better.
So, I mean, you looked at the sort of Shirley-Adams,
Right.
But there are other
Right.
that are said.
Right. So I wouldn't want to claim it 100%, but this is one of the referees of our paper said that we've actually proved it for SDPs. Well, we don't know whether we have, but here's one thing: we can PP interpret equations, and its equations are not only not solvable by Shirley-Adams, but they are not solvable by SDPs. This is Schoenberg's result from a few years ago, which was actually a rediscovery of all the results of someone improved complexity 15 years ago. So the only thing you need to do is to show that all these reductions we do preserve SDP solvability. But you have to be careful because the kind of reductions we use are more general than the ones used in the approximation community. But assuming we can just go through the proof and check that all these, say, interpretation using opt fees and all these operations we do, they do not mess up SDP solvability, the result would be that for any valid constraint language, if you care about exact solvability, either you are solved by the third level of Shell-Adams, or you are not even solved by linear levels of Lassere hierarchy. I mean, we only look at LPs because we wanted to get a dichotomy out of it, and it's not even clear if you have a non-constant level of linear program relaxation. What does it tell you? It's not a polynomial time algorithm straight away. But
any other questions? Okay, let's go.